Hello. Today, we begin our study of automatic identification and tracking technologies in logistics.
Modern supply chains are complex global ecosystems. Managing them is impossible without absolute transparency of information flows. From the moment a product is shipped from the manufacturing plant until it reaches the end consumer, every action must be recorded quickly and accurately. We will examine the evolution of the tools that provide this transparency, how basic barcodes, which revolutionized accounting, are gradually being supplemented and replaced by two-dimensional matrices, radio frequency identification tags, and extensive Internet of Things ecosystems. Understanding these technologies is critically important for building efficient warehouse logistics, controlling multimodal transportation, and minimizing financial losses. Our goal is to thoroughly analyze the operating principles of each technology, as well to assess the economic feasibility and fundamental physical limitations of their implementation in real business processes.
The main enemy of efficiency in any logistics information system is manual data entry. When we rely on a warehouse worker to manually type, for example, a long product SKU on a keyboard, we are consciously accepting low speed and a high level of risk. According to statistical studies, human error causes one mistake for every 300 entries. For automatic identification technologies to work seamlessly on a global scale, a single standardized language is necessary. This function is performed by the international organization GS1, which guarantees the uniqueness of every code in the world. In logistics practice, it is important to clearly distinguish between two basic types of linear barcodes that perform completely different tasks. The first is the EAN13 retail code, which you see on consumer goods in stores. This identifier is static. It encodes only basic information: the country of registration, the manufacturer, and the product SKU itself. However, for full-fledged warehouse management, this data is critically insufficient, as the system does not see the life cycle of a specific product unit. For managing warehouse flows, a specialized logistics standard, GS1-128, is used. Its fundamental difference lies in its ability to encode dynamic attributes. Thanks to this standard, we can capture a specific batch number, the exact production date, and the weight in a single barcode. The presence of such extended data is a mandatory technical requirement for implementing complex logistics operations, particularly the FEFO shipment strategy, where the product with the nearest expiration date must leave the warehouse first. Let's examine the internal structure of a GS1-128 standard logistics label in more detail. Its main technological advantage is the use of application identifiers, which are special prefixes in parentheses that serve as instructions for the information system. Thanks to them, a long string of numbers is transformed into a structured set of data. For example, the prefix 01 always denotes the GTIN, a unique 14-digit identifier for the product itself. Dynamic data, which changes from batch to batch, is of particular value for warehouse accounting. The prefix 17 indicates the expiration date, which is recorded in a strict format: year, month, and day. Thus, the number combination 251231 is instantly recognized by the system as December 31st, 2025. In turn, the prefix 10 allows for encoding the production batch number, which can contain up to 20 characters. It is fundamentally important that during scanning, the WMS system does not just read the numbers, but automatically parses the array into separate logical fields. A single scan provides instant access to all necessary information about the product, its series, and its life cycle. This completely eliminates the need for manual entry of dates or batch numbers, guaranteeing impeccable data accuracy in the system.
Linear barcodes have a significant physical limitation: low data density. They take up a lot of space on a label, but contain minimal information. Therefore, modern logistics is shifting from linearity to density by implementing two-dimensional formats, with the data matrix code becoming a key one.
This format allows for storing thousands of characters in a few square millimeters. This technological advantage has revolutionized serialization, i.e., the transition to item-level tracking. Whereas previously an entire batch of medication might have a single identifier, today every ampule in the pharmaceutical industry receives its own unique tiny data matrix code. This makes it possible to track the life cycle of a specific product unit from the conveyor belt to the patient, which is critically important for ensuring quality and absolutely necessary for combating counterfeit products. The change in labeling format has also forced an update in reading tools. Traditional laser scanners can only process linear 1D codes, require a strict scanning angle, and are completely powerless against device screens or damaged labels. The modern industry standard has become image-based scanners. They work like digital cameras with machine vision algorithms. They easily capture both 1D and 2D codes, read partially faded or damaged symbols, and most importantly, instantly recognize information from displays. The latter is extremely relevant for the rapid processing of electronic bills of lading when receiving goods from delivery drivers. A fundamental obstacle to further optimization of optical scanning is the line of sight requirement. In a warehouse environment, this places a significant burden on personnel. A stockkeeper must manually find and read each label. When dealing with hundreds of items on a single pallet, this process becomes critically slow. Radio frequency identification technology, known as RFID, completely eliminates this drawback. Its key feature is that radio waves can pass through most packaging materials: cardboard, plastic, wood. This means the system can identify a shipment even if it is inside a closed box or under a layer of protective film. The lack of a need for visual contact with the tag fundamentally changes the approach to inventory management, allowing for remote and bulk data reading without wasting time searching for each individual barcode. The physical principle of radio frequency identification is based on the continuous interaction of two key system components, the reader and the tag. The reader is an active element that constantly generates an electromagnetic field. The tag itself, which is attached directly to the cargo, has an extremely simple structure. It consists of a miniature antenna and a microchip that stores data, including the unique electronic product code, or EPC. From an engineering perspective, the most interesting aspect is the power and data exchange mechanism. Let's consider a basic passive tag, which is the industry standard for tracking pallets or boxes in distribution centers. Such a tag has absolutely no built-in battery. It remains inactive until it enters the electromagnetic field generated by the reader. As soon as this happens, the tag's antenna captures the energy from this radio wave. This induced microportion of energy is sufficient for the microchip to wake up and instantly send its response with the identification data back to the reader. This elegant technological solution, where energy is drawn directly from the air, allows information carriers to be made as compact as possible and eliminates the problem of dead batteries on the scale of a warehouse with many thousands of items. The evolution of information carriers in logistics has progressed from simple passive tags to intelligent, ambient Internet of Things systems. To understand the technological choices, it is important to distinguish between three main classes of identifiers. The most common are passive RFID tags. They have no internal power source and are limited to a read range of up to 15 meters, but their low cost makes them ideal for labeling individual boxes or pallets. In contrast, active tags are equipped with a built-in battery, allowing them to transmit a signal over a distance of more than 100 meters. This is an expensive solution, used exclusively for tracking high-value assets, such as sea containers or vehicles in large open terminals. A real breakthrough was the emergence of ambient IoT, particularly battery-free BLE tags. Their uniqueness lies in their ability to harvest microenergy directly from the surrounding environment, from Wi-Fi, Bluetooth, or cellular signals. This technology effectively blurs the line between cheap passive tags and complex monitoring systems. The implementation of battery-free sensors allows any logistics hub to be transformed into a continuous smart environment, where the movement of every item is tracked continuously and accurately, at any point where there is at least a minimal radio signal.
A fundamental advantage of radio frequency identification over traditional optical scanning is the ability to perform bulk data reading. Imagine a standard warehouse operation. A forklift moves a pallet containing 100 boxes of various goods. Instead of manually scanning each individual unit, the equipment simply passes through special RFID gates. In literally 1 second, the information system recognizes all the tags simultaneously and instantly compares this actual data with the electronic shipping note. This provides absolute cargo verification without any interruption to the logistics process and completely eliminates manual labor at this stage. An additional benefit is the extraordinary physical durability of the identifiers themselves. For example, a tag can be discreetly sewn into the lining of a jacket, making it protected from damage or dirt, unlike paper labels. This same technology has revolutionized the speed of warehouse inventory counts, ensuring the complete autonomy of this process. Lengthy walks through aisles with handheld terminals are gradually becoming a thing of the past, and the modern industrial standard is drone-based inventory. Specialized drones, equipped with machine vision systems and high-speed readers, can operate at night, autonomously navigating between rows and ascending to the upper, 6th or 7th storage tiers. As a result, these devices read thousands of tags per hour without any human intervention and instantly synchronize the actual stock levels with the warehouse's WMS data.
A logical question arises. If radio frequency identification technology is so effective, why hasn't it completely replaced traditional barcodes yet? The answer lies in two fundamental limitations: economic and physical. Let's start with economics. Printing a standard paper barcode costs a fraction of a cent, whereas the cheapest passive RFID tag will cost a company at least 4 to 10 cents. When labeling consumer electronics, such as a $500 television, this additional expense is entirely justified. However, attempting to affix a 10-cent tag to a bottle of drinking water with a purchase price of 15 cents becomes an outright economic absurdity. The high cost of the tag itself makes this technology economically unviable for cheap, fast-moving consumer goods. Furthermore, a company must be prepared for significant capital investment in infrastructure, installing reader gates, purchasing special terminals, and complex software integration of data arrays into the warehouse management system. The second barrier is related to the laws of physics. Radio waves interact very specifically with certain types of materials. Metal surfaces act as a shield, reflecting the signal, while liquids, conversely, completely absorb it. Consequently, any attempt to read a standard passive tag attached to a metal barrel filled with water or chemicals is guaranteed to fail. To identify such cargo, specialized shielded solutions must be used. They successfully overcome the physical obstacles, but their high price brings us back to the problem of economic feasibility. Barcoding and radio frequency identification technologies ensure that cargo is recorded at specific nodes in the supply chain, but they do not provide a complete picture of what is happening to the goods during long-haul transportation. It is during the transit stage that blind spots most often occur, where the logistician loses control over the condition of the assets. The solution to this problem is the concept of the Internet of Things, or IoT, which transforms the transportation process into a completely transparent environment. The Internet of Things in logistics is an extensive ecosystem of intelligent sensors and telematics devices that continuously collect data on the condition of the cargo and autonomously transmit it to information systems via cellular or satellite networks. If an RFID tag answers the question, "What and where was this at a specific moment?" IoT tools answer the critically important question, "Under what conditions is the cargo right now en route?" The system monitors the temperature inside the truck body, the vibration level, which is important for high-tech equipment, and the vehicle's movement dynamics in real time. This continuous data stream allows companies to guarantee delivery quality throughout the entire route. In the logistics of climate-sensitive goods, such as pharmaceuticals or food products, it is critically important to ensure the continuity of the cold chain.
Traditional monitoring methods, based on the use of standalone data loggers, have a significant drawback. The data from them can only be retrieved after the truck arrives at its destination. This means the company learns about a temperature violation after the fact, when the cargo is already spoiled and the losses are inevitable. The Internet of Things technology fundamentally changes this model, allowing a shift from acknowledging losses to proactive management. Smart sensors continuously monitor the environmental conditions in real time. As soon as the temperature readings go beyond the established safe zone, the system instantly generates an alert for the dispatcher and the driver. This makes it possible to take immediate action, remotely adjust the refrigerator settings, or promptly direct the vehicle to a service station. As a result, the batch of goods is saved, and the company avoids huge financial losses. To guarantee absolute trust among all supply chain participants, data from such sensors is integrated with blockchain technology. The readings are recorded directly into a distributed ledger, where they cannot be deleted, edited, or falsified. This creates legally significant and transparent proof of continuous compliance with the temperature regime, which is critically important for the certification of high-value medicines and for ensuring the safety of end consumers.
In addition to climatic parameters, modern smart sensors provide digital control over the physical handling of cargo and its security. This becomes critically important when transporting fragile products, complex electronics, or expensive industrial equipment. To monitor mechanical impacts, accelerometers and gyroscopes are installed directly on the cargo or container walls. Let's consider a practical situation. During cross-docking, terminal workers drop a box with a high-tech server or turn it upside down despite the warning labels. A smart sensor instantly records the exact time of the incident and the impact force in G-force equivalent. Thanks to this objective data, the logistics company can indisputably identify the responsible party at any stage of a multimodal route, no matter how complex, and promptly initiate an insurance claim. Another important aspect of continuous monitoring is protection against unauthorized access. Door opening sensors are synchronized with a geofencing system. If the doors of a truck or sea container are opened outside an authorized location, for example, during a night stop at an unsecured parking lot, the system immediately generates an alarm and automatically notifies the security service. This minimizes the risk of theft. The comprehensive use of such solutions transforms a transport vehicle from a closed black box into a completely transparent environment. The business gains an effective tool that allows it to move from acknowledging losses after the fact to systematically preventing them.
In modern high-speed supply chains, the speed of data processing becomes as critical as the physical speed of transport. The traditional Internet of Things architecture assumes that all data collected from a truck's sensors is sent to a central cloud server for analysis, after which the system returns a management decision. However, in critical situations on the road or during maneuvering, a signal delay of even a few seconds can lead to irreparable consequences. This is why logistics is transitioning to edge computing technology. Its essence lies in moving the analysis of vast data arrays directly to the edge of the network, that is, to the onboard microcomputer of the vehicle itself. The deployment of fifth-generation 5G networks provides the necessary bandwidth and minimal latency for instant communication between smart sensors. Let's consider a critical scenario. During transit, a multi-ton steel coil suddenly shifts in the cargo bay, threatening to overturn the truck. Telematic sensors detect the change in the center of gravity and motion vector in milliseconds. Thanks to edge computing, a mathematical model makes the decision for emergency automatic braking or suspension stabilization locally without waiting for a connection to a remote server. This instantaneous reaction allows the system to prevent an accident faster than the driver can even realize the danger. This elevates transportation safety to a qualitatively new level where decisions are made in real time directly at the scene of the event.
Summarizing the evolution of tracking technologies, we can identify three conceptual levels of logistics transparency. The base level is barcoding, which provides primary identification and answers the fundamental question, what is this product? The next level is formed by radio frequency identification, RFID technology.
which brings mass automation and provides an understanding of where exactly is it located. The pinnacle of this evolution is the Internet of Things, IoT, which provides constant context by answering the question, what is the condition of the cargo right now? This development clearly demonstrates how modern supply chains are gradually and irreversibly eliminating blind spots. Whereas information was previously collected fragmentarily and depended on manual labor, today the information flow moves inseparably with the physical cargo. We are witnessing the final blurring of the lines between the virtual information system and the real physical world. Every pallet, every shipping container, and every truck becomes an active participant in data exchange. Thanks to this, a fundamental managerial shift is occurring, from reactive, post-factum observation of events to the construction of fully proactive systems. Modern technological solutions are capable of independently sensing the external environment, analyzing risks, and reacting with lightning speed to critical changes without any human intervention.
This concludes our lecture on automatic identification and tracking technologies. Thank you for your attention.